again here. If you want to find your notes. And you guys in the hall, if you want to come back on in. So this is our last section. Wait, you guys good to go? So I got 40 minutes left here. It's not an overly long lesson. This is our last one though, so I just want to remind you guys of a few things. Today, I gave you guys an extension. I need your lab by the end of the day though. I want to start marking those ASAP to get them done. Okay. I'm not going to take them late though. We talked about that a lot yesterday. So make sure they're done before like the end of the day. Okay. Tomorrow's going to be a work day. And then on Wednesday, we're going to do a lab. Thursday, we're going to have a work day. Next week, Monday, we're going to have a lab. Yeah.
You said tomorrow we have a work day and then Wednesday we're going to do a lab.
Sorry, Thursday, we're going to do a lab. So, work day tomorrow, Thursday lab, Friday work day, Monday lab, 2 labs almost back to back. And then, have you guys seriously not printed off notes yet?
I did, but hopefully lost time.
Hopefully.
You're going to be kidding me. It's 11 o'clock. Monday we're going to do a lab next week, and then it's going to be pretty busy next week. It kind of sucks, but it's the way I try to end all of our units. Tuesday we'll do a quiz, but the quiz may as well be a unit test because it's on everything. Then Wednesday I'll give you guys like a break day so that if you don't do well on Tuesday's quiz, then you can hopefully learn from your mistakes, and then Thursday we'll do a unit test. Long story short, this next week and a half is going to be kind of busy. So you guys make sure you plan your time wisely because you got a lot of things to work on. And we're going to change the way we do like progress logs. I'm not going to let you guys just intentionally take zeros on things. Like want you to hand everything in. The idea behind progress logs was that you do everything and you get rid of your worst marks rather than just not do stuff. Yeah.
You said except maybe the
Except the project. I'll understand the project. That one's a little bit different. Okay. Project is a good way to help maybe increase your mark. I mean, it's going to take a lot of work, but I mean, if you spend some time on it, I can show you some exemplars. Raj has been doing a few of them for my grade 12 classes, and I mean, he says it takes him about 4 or 5 hours, but he's gotten some excellent marks, which helps pull your grades up. So, if you're willing to spend 5 hours on research, so yeah, like he wrote like a 10 to 12 page paper though. So well, actually. I would actually say, maybe in your case, actually you should, because you want to go into nursing, right? And that is going to be an expectation in nursing, is that you write on a regular basis, like a 10-page paper. And that was one of the ideas I had behind these research papers, is if this is something you want to do in life, it wouldn't hurt to practice writing papers now. You know? So, I mean, yeah, it's going to make you busy, but I mean, you're also in a high-level -1 chemistry class, so if you're afraid of spending 5 hours doing work, then, you know what I mean? That's the issue, right? Okay. Does that make sense going forward? Okay, let's do our last topic. One of the things that I was thinking of when I did these questions here is that they're kind of unrealistic. And one of the reasons why they're unrealistic is these conditions right here. What does STP stand for? Okay, so standard temperature and pressure. What is that standard temperature?
0 degrees.
0 Celsius.
Is it ever 0 degrees Celsius?
I mean, let's say you're starting your car. Maybe it was cold outside and you started your car and it might have been at 0 degrees Celsius. But after a while, isn't it going to warm up?
Yeah.
And as you combust stuff in your vehicle, isn't the temperature going to increase? And then maybe the same thing here. Like, say you're doing the propane tank. I said SATP conditions. That's 25 degrees Celsius. So that's like a warm summer day. But like, okay, but again, let's say you start combusting some of these gases here. Is your barbecue at 25 degrees Celsius the whole time? I mean, eventually it's going to be up to 2, 3, maybe 400 Fahrenheit. So it's going to change. And that's what I want to focus on today. Yeah.
I tell you what, my truck runs 1200 degrees Fahrenheit.
Okay, so considerably warmer, right? The point I want to make here, though, is that SATP and STP are helpful sometimes, but what if we're not under those conditions? Can we still solve questions that involve going from liters into grams. Does that make sense? Or from grams into liters. Because that's more or less what we were doing in these questions. Is I gave you a gram number, said find me a liter number. Or I said here's a liter number, find me a gram number. But it all hinged on it either being this value or this value here. So what we're going to talk about today is called the ideal gas law, and it can be done under any temperature, any pressure, any volume. Before I start though, just a quick review. What is an ideal gas? Well, here's some properties of ideal gases. These are things that gases should always do. They should always be in movement. They should always move constantly and randomly. The mass of the actual molecule, not relevant. Kinetic energy is conserved. They don't attract each other. Those are ideal gases. When do gases stop becoming ideal and they become real instead?
High temperature, low temperature,
Flip that.
high pressure.
Low temperature, high pressure. So these laws that we're going to talk about, they're going to work for normal conditions. But if I were to give you like a temperature of like 4 degrees Kelvin, okay, this law doesn't work actually. And if I were to give you a pressure of like 5,000 megapascals, these laws might not work. But so long as we're talking about reasonable gases, all of these laws should work. And so here are the laws we've learned so far. First law is Boyle's law. Pressure times volume is always equal to a constant. Second one is Charles' law, which actually is volume over temperature equals a constant. I have that one backwards. And then the last one was about Avogadro, which is kind of what we talked about yesterday. Volumes over moles, like liters over moles, equals a constant. Long story short, we can actually shove all of this stuff together in one like super formula. And this is that formula. It's actually really easy to work with. Maybe I'll skip a slide though. It's right here. This is the formula that combines everything together. And I like to call it PV equals NERT. NERT. That's what I was told when I was younger, and it's stuck with me actually, since I'm even teaching it now. So if I ever talk about PV equals NERT, this is the formula. It is known as the ideal gas law. Let me just go back a slide though. We've discovered that PV equals a constant, V over T equals a constant, and V over N equals a constant. We've actually calculated this constant. It is 8.31. I'm going to write that down somewhere because we're going to use that a lot. The lab we're going to do later this week, actually, we're going to actually prove that this number is 8.31, hopefully.
This is R.
This is known as R. R is the letter we use for a constant. I can actually prove where R came from. Let's substitute some of the STP values into the equation. So STP means that you would have 101.325 kilopascals. And we know how many liters there are at STP. It's 22.4 liters in 1 mole. And then this 273 Kelvin, that's 0 Celsius. So if you plug all these in together, this number comes out to be 831. And we're going to use this in the formula a lot.
Is that the constant?
Yeah.
You mean to write the other stuff next to it? Is that
Probably not, but I would definitely write this down. So, let me show you some examples. It's actually not really that hard to do. Let's say that we use 31.6 liters of gas. And I wanted you to try to find how many moles of gas there were. Well, what we did earlier today is we said, well, 31.6 liters, we'd just multiply by a mole per liter, and you'd say throw in like a 22.4 liters. Ta-da, you're good to go. Here's the problem. This number right here only applies under 0 Celsius and 101.325 kilopascals. What if you're not using those values? Then everything I showed you earlier today is actually useless. And we have to do PV equals NERT instead. So it's a pretty basic formula though. I want to get N by itself. How do I get N by itself?
Divide over R.
Okay, so you need PV over RT equals N. And we actually have every single value you need. We have a pressure, so that's 127.6 kPas. We have a volume, 31.6 liters. R,
That's the 8.31.
memorize that or write it down somewhere. By the way, we should write in the units for R. The units are kPa, liters, over mole, kelvins. Last thing here, we need to know a temperature. Well, it was 77 degrees Celsius.
What do you need to count?
I need it in Kelvin, so I got to add 273. So is that 350? I'm going to recommend you write in your units because you should see how the units work now. Kelvins will cancel. Liters will cancel. Kilopascals will cancel. What's the only thing that didn't cancel? Fantastic, moles. Nice, so calculator time. Take 127.6 times by 31.6. Divide by 8.31. And also divide by 350. I might recommend put the top and bottom of the fractions in brackets so you don't screw it up your calculator. Anybody get that value? Does that work? Well, that tells us how many moles we have. Do we normally stop at moles? Usually we go to grams. This question here, though, I just said find out how many moles there was. But in theory, what we could do then is take this moles number and convert it into grams by just using a molar mass. The only question would be is, well, what's the molar mass? Well, it depends on what substance it is. In this question here, though, I didn't tell you what substance we used, so we're done, I guess. Does that make sense, though? But in theory, in other questions here, we could times by a molar mass if we know what the gas is. So this is the way that we convert from liters into grams if it's not at STP or at SATP. Does that make sense? It's a pretty straightforward formula, to be honest. Any questions? Okay. So let's try a more purposeful example here. Here I'm going to give you grams. I'm actually also going to give you liters. I'm going to give you temperature. Now I actually want us to find pressure. We work backwards and solve for something different. So start with your formula. PV equals nert.
Divide over the page.
That was like saying nert. Okay, so if we want pressure, we got to divide over V. So I need to know four things. I need to know an N, an R, a T, and a V. I know R. R is 831 kilopascal liter over mole kelvins. No, a temperature. 25 Celsius is 298 Kelvin. I even know a volume. The volume's in milliliters, though. I gotta put it into liters. What's it gonna be in liters? Like even smaller.
It's less than 1 milliliter. It's like
It is a very, very, very small amount of gas, I guess I have here, right? Right. So, like, maybe another way of putting this would be to go 0.0, then add 3 more zeros. Like, this is a very, very small amount of gas. Right? Like, infinitely small. I'm missing a number, though. I never actually put in a value for N. I have to find that. I was given a mass, but is a mass the same thing as a moles? Sadly, no. How do you convert mass to moles, though? Well, 30 grams. If you do a mole over gram, that'll get you moles. So this is kind of similar to what we did earlier today. Where am I going to find that gram mole value?
Neon. That's the neon gas.
All right, so what's neon's molar mass? 2018?
Or 20.
So 20.18. So So if I take this mass and I divide by the molar mass, I should be able to get a mole number. Hopefully. I'm guessing probably 1.5 moles or 1.6 moles. 1.48 I got. Alright, so last step. Now that I actually have a moles number, I can actually throw it into this equation. That was the one thing I was missing. So our moles should cancel. Our liters should cancel. Our kelvins should cancel. What's the only thing left? kPas. It's the only thing left. Which is good because it asked me what the pressure of the gas was. So, finish off this calculation. 1.48, we got to times by 831. We got to times by 298. And then divide by a very, very small volume of gas. 1, 2, 3, 4, 193. 190748034.5 is what I got. Yeah, I have a couple of points I want to make on this one. I picked this one kind of purposefully. First one is I wanted to make sure you guys remember to convert milliliters to liters correctly. Secondly here, this as a kilopascal might even be it's a lot of kilopascals. Should the ideal gas law probably apply in this scenario here? Why? Because the pressure is really, really high. I mean, think about this here. You've got a volume that is like this big for volume. And inside of that volume, you've somehow crammed in 30 grams of gas. The only way you're going to cram that much gas in there is if the pressure is insanely high. But will this thing really act like a gas at this point anymore? No. So the truth is, sometimes afterwards we might look at our pressure value and say, this probably isn't really valid. Because it's called the ideal gas law, and this probably isn't going to behave as a gas at all. So I wanted to point that out, is sometimes we might discover that our value is kind of unreasonable. We actually don't have a way of calculating it otherwise, but I might ask you a question and say, is this an ideal gas? And then you'd say, no, this is not going to be an ideal gas. Is there a number that I'm looking for? To be honest, no. But I mean, if the number seems really excessive, hopefully you'd agree that this number here is pretty crazy. We should round it properly, though. How many sig digs do I get? 25 degrees Celsius. Looks like it has 2. But I change it to Kelvin, so it actually has 3. So I think I get 3 sig digs. So 1.91 times 10 to the 8 kPas. So a lot of pressure. Enough that this thing will not behave as an ideal gas. Make sense? Cool. Last one, I think, right? Okay. So here's a typical example where I'm giving you grams and I'm saying find me volume. If it's an STP or an SATP, we use that 22.4 or 24.8 number. But we're not at those values, so we have to use PV equals NERT. So let's try it. PV equals NERT. How do I get volume by itself? Okay. Okay, so I need a couple of things. I need to have a moles. I need to know an R value, which is always the same, a temperature value, and a pressure value. Do I have moles?
That's a special one. You like because you're only using 36 by 2 grams of nitrogen dioxide, and you have to divide by the actual to that.
Good. So we need to divide by the molar mass. What is nitrogen dioxide's formula? Nitrogen, N, oxide, O2. There we go, NO2. That's nitrogen dioxide. I got 46.01. So whatever that equals is going to be my mole number. So I'm just going to draw an arrow and drop it in there. Then I need R. 831. kPa liters over mole kelvins. Temperature 260. I gotta add an extra 273 to it. So what is that? 533. What about the bottom? Can I just throw a 60 on the bottom? Because that's pressure. I need it to be in kPa, and this is in atmospheres. By the way, 60 atmospheres? That's also a lot of pressure. Because each atmosphere is 101.325. So like it's 60 times 101.325. Let me just write that down here. 60 atmospheres multiplied by 101.325 kPas in an atmosphere. So that's actually a lot of pressure as well. That number is going to go here. Yeah. So 6,000 kPas. Again, you might be able to argue and suggest maybe this shouldn't be an ideal gas because that's a lot of pressure. And that's one of the things you might recognize is that this formula does not work if the pressure is exceedingly high or the temperature is really low. But we'll try it anyways. So, let's put all these numbers together. If I do my 32.6 divide by my molar mass.
You said it 32.6, but it's 36.
Oh, thank you.
I don't know if you.
Thank you. So 36.2 divided by my molar mass. I get about 0.7867. I'll just write that in here. 0.7867. I'll use all those values though. And I'm going to times by 831, times by 533. Then I've got to divide by like 6,000 or something like that, right? Okay, so long story short, I got 0.5732. Anybody else get that? Let me just check my units here. This liters right here is the only thing that shouldn't cancel because this is a mole that'll cancel with this mole. This is a kPa that'll cancel with that kPa. I already canceled kelvins, so this should be in liters. So sig digs, how many sig digs do I get? Actually 2 in this one, because the 60 atmospheres, that one actually only does have 2. So I would say that it needs 0.57 liters. Am I done? Actually, I'm not. I'm gonna be really careful here. It just said that we decompose nitrogen oxide into its elements. How much volume of total products would we expect? I'm not actually even done the question yet. What would decomposing nitrogen dioxide look like? Well, what would it make? It would make N gas, and it would make O gas. How do I balance this thing? Let's see, I probably think I need a 2 of these guys here. And a 2 here. How does this apply to our scenario now? Well, if this guy is 0.57 liters right here, how much oxygen would you expect? Same amount, right? Because if this guy's a 2, that guy's also going to be a 2. But how much nitrogen would you get? How much did you say?
I said half.
Half is right, yeah. Because, I mean, if this is a 2, and this guy is a 1, you'd get half of 0.57. So, whatever that is. 0.2. I guess when I round it, I get 0.29. So how much total products will you get? I got 0.86 of total products. Did that last step make sense, by the way? Because it was kind of a twist ending to it. Is we didn't just stop with the 0.57, but we had to then figure out, well, how much of the two products do you get? And this is another one of those examples where when it decomposes, it actually gives off more volume than it started with. That follow?
Yep.
Okay. Questions, comments, concerns, conundrums, curiosities, complaints, criticisms, critiques, queries? No?
How entertaining.
All right. I'm done. Actually, that's our unit. To be honest, there's only 6 topics in the unit. Okay. So, if you guys need something to practice on this particular topic, here's some notes. Going forward, though, we got a lot to do. Like I said, 2 labs, a quiz, a unit test, an assignment, a project if you so want to. And guys, I need your labs by the end of the day, okay? I want to try to mark those as soon as I can. Does that work? So I know you only have about 10 minutes left, but try to do something productive in that last 10 minutes, okay?